So, as we look back at exponential functions, I want to actually examine a definition here. Since we've been talking about inverse functions, the definition of the natural exponential function, or e to the x. All right, the inverse function of the natural log function, f of x is ln of x, is called the natural exponential function, f inverse of x equals e to the x. All right, and here you have kind of the relationship, all right, y equals e to the x if and only if x equals ln of y. Okay, and you may have learned that back in your algebra classes or whatever, is just rewriting an exponential as a logarithm or rewriting a logarithm as an exponential. And we know that that applied to other bases as well. For example, when you had a log base 2 of x equals 3, you then would rewrite that where 2 is the base, 3 is the exponent, and the argument inside the log is what that equals. Okay, so you would rewrite those logarithmic equations as exponentials in order to solve them. Okay? So this inverse idea applies not just to natural, but any log with log bases. And you've seen that part before. Okay? But now, hopefully, the wheels are turning in your head a little bit since we've recently talked about inverse functions. Think about how this could come into play with the derivative of an inverse is 1 over f prime of g of x times equals the g prime of x. Okay, so here you can actually find derivatives if you know the inverse function. But just kind of putting that together here. So that's kind of a little further on down the road here. So notice because of the inverse relationship that when you graph these, you get the mirror image across the line y equals x. You know, down here you have the point 1, 0. And that means on its inverse we have the point 0, 1. Okay? And, you know, over here we have the point E1. And on this one we have the point 1e. Okay, and you can go on from there. All right, but let's just run through a couple quick examples of solving some of these equations. So I want to make sure that we have this basic skill down before we start doing derivatives and stuff. Okay, so if I have 7 equals e to the x plus 1, what do I do with that? Yeah, take the ln of both sides. So ln of 7 equals ln of e to the x plus 1. And how does that help us? Yeah, ln of 7 equals x plus 1. Now, how you think through this logically is up to you, but if you think of this as the inverse function, okay, the ln and the natural exponential, the e to a power, will undo each other, and we get just the exponent left over. You could also see this as pulling the exponent out in front times ln of e, and you know ln of e equals 1. All right, so however you think through that, you'll get the same result, that this side is just x plus 1. So now we have here x is just a negative 1 plus ln of 7. Okay? And that's as simple as we can make it without a calculator or a table of ln's or something. Okay? How about right here? ln of 2x minus 3 equals 5. What am I going to do with that? Okay, I get what you're saying there. Yeah, we would have e on both sides, and we would make what's on both sides the exponent of e. That's what you meant? So ln e to the ln of 2x minus 3. Okay? And then, as a result, e to the ln will undo each other, and we have 2x minus 3 equals e to the 5th. At that point, it's basic algebra. Add 3, divide by 2, and x is e to the 5th plus 3 over 2. Okay? Remember, an alternative way of thinking through this is to see this as it is, the log base e of 2x minus 3. And as I was saying before, we can rewrite this based on what a logarithm is. A logarithm is saying that e, okay, if that's our base, it's saying that 5 is the exponent of e that will give us the argument, 2x minus 3. Again, however you figure that out, you'll get to the same place. Okay? But we do want to keep in mind that these are inverses. All right. So, all right. So let's think about differentiation at this point. Okay? Don't forget the different properties of the natural exponential function. We have the parent function, e to the x, you looked at last year. The parent function, the domain is all real numbers. You can put any number in as an exponent of e and you'll get a real number. So the domain's all real numbers. However, the range is from 0 to infinity, because remember there's a horizontal asymptote at 0 as x approaches negative infinity. Okay? Now, because of how it looks, we can also see, notice it is continuous, it's increasing. And because it's increasing over its whole domain, it's also 1 to 1. That's what makes it have an inverse. Okay, remember it has to be 1 to 1. Yes?
How do you get 0 out of e to the x to the range?
It actually has to do with, it actually kind of goes back to Bobo-Botten if you think about it. If I had a negative exponent, let's say e to the negative 10th power, okay, that's 1 over e to the 10th. It's kind of a similar idea as Bobo-Botten, where the bigger on bottom makes it go to 0. Here, e to a power is going to continue to get bigger and bigger and bigger. So if it's 1 over e to the power, it's 1 over something huge.
Okay, so it's not saying that it's ever going to get to 0. It's just
no, it will never actually equal 0, but there's that asymptote.
Okay.
There's an asymptote there. Okay. It says that the graph of e to the x is concave upward on its entire domain. And then also notice the limit as x approaches negative infinity is 0. That's why we have that horizontal asymptote. As we go to positive infinity, though, it's going towards infinity. Okay? Now, a rule that we have looked at in the past is this derivative of e to the x is e to the x. Okay? I want to use that actually to prove a couple of the things that we just stated. Alright? We know e to the x is continuous. How do we know it's increasing on its entire domain? Well, if I have f of x equals e to the x, f of x, f prime of x, we just said is also e to the x, right? Well, we already know that that will always be positive, okay? F prime does not equal 0 anywhere, so the sign diagram looks like this, okay? There's our number line, nothing goes on it. Pick any number, We plug it in, we get a positive. So there's our sign diagram. The function is increasing over the entire domain, which is all real numbers. Okay? How do we know number 3 up there? It's concave upward on its entire domain. Well, what's the second derivative? It's also e to the x. Okay? The second derivative will never equal 0, so I know concavity never changes. And our sign diagram for that also looks like this. But that's telling us that since it's positive everywhere, the function is concave up for all real numbers. Okay?
Mr. Jackson,
Yes?
say you are not giving the interval. Can you say that the relative minimum is approaching 0 or equal to 0?
Well, this one, there would be no relative minima or maxima, because to be a relative max or min, it has to be at a critical point. Okay? Anytime we talk about absolute max or min, like for example, this one, you couldn't really say, you would have to say that the absolute min is approaching 0. So it wouldn't really be real helpful if we looked at the whole domain. It would be more, okay, if we looked at an interval, say from 1 to 5, we actually know that the absolute min on any interval will be the leftmost point, the lowest value of x. Okay? So that's a good question, but in this case we would need some kind of an interval for it to really make sense. Yes?
So if it asked what the absolute minimum was, just on the whole graph, would you just say approaching 0 pretty much?
Yeah, you'd have to just say it's approaching 0 as x approaches negative infinity or something like that. Okay? Good questions. Alright, now that's e to the x. We also looked at here, if we have e to a function, e to the u, it's going to be e to the u times the derivative of u. And that is our chain rule, okay? That's our chain rule. So, let's practice a few of those, okay? If I have the derivative of e to the 2x minus 1, what's this going to be? Can someone... e to the 2x minus 1 times 2. Okay, times the derivative of 2x minus 1. Okay? Everyone got that? Alright. Okay, so here we have e to the negative 3 over x.
E to the 3 over x times negative 3 over x squared.
Almost. Almost. You're doing the derivative.
It would be 3x and negative 2.
Of
3 over.
negative 3x to the negative 1. You just had a negative off.
Oh.
But you were on the right track there. Yeah, so times the derivative of that, so it is a positive 3x to the negative 2. Okay? So that we have e to the negative 3 over x times a positive 3x to the negative 2. We could rewrite that if we like. Since both of those parts have negative exponents, we could actually write this as 3 over x e to the 3 over x, if we wanted x squared, e to the 3 over x, if you want to write it without negative exponents. Okay? Not too bad, right? Some good review for us, all right? We want to make sure that this skill we have down really, really well before we move on. Okay? So, that is it. At this point, it's just a matter of some practice. Okay? So that's what I'm going to spend the rest of our time doing here. Let's practice, get this down really, really well, and then we'll move on in the days to come. Okay?